The story of barcodes begins with a need to make simple tasks repeatable and reliable. Retailers wanted faster checkouts and fewer mistakes when scanning price and product information. Warehouses sought ways to track large numbers of items through receiving and shipping. Manufacturers needed standardized labels that could travel across companies and borders. Early thinking about machine-readable markings came from experiments in automating identification. Simple patterns of light and dark were easier for machines to detect than handwritten numbers. Designers worked to convert visual contrasts into digital signals that computers could interpret. Those efforts gradually led from paper lists and manual checks to machine-readable symbols. The idea was not to replace human judgment, but to reduce repetitive work and error. Over several decades, those ideas grew into formalized sets of rules and visual forms. Standards would later shape how codes looked, how data was encoded, and how scanners read them. Before barcodes became common, merchants relied on printed numbers and clerks who memorized prices. Inventory lists and ledgers were updated by hand after each sale and shipment. The manual process worked for small stores and limited stock, but it did not scale. As retail grew, so did the time spent counting and reconciling items. The logistics of larger operations exposed the need for a consistent system. Postal services and railways experimented with coded labels and punched cards for routing. Those parallel efforts influenced ideas about using visual marks on packages. Engineering teams took inspiration from telegraphy and early computing to make marks that machines could quickly parse. The concept focused on translating physical marks into binary signals for electronic systems. That pathway from human-readable numbers to machine-readable bars and spaces set the stage for later standards. The early technical work on barcodes explored simple linear patterns and their detection. Inventors tested various widths of stripes and gaps to find reliable contrasts. Experiments included patterns that encoded only a few digits and others that offered more flexibility. Researchers concentrated on scanners that could measure reflected light and convert it into electrical signals. Early scanners used incandescent lamps and photodiodes to sense contrast. Robustness mattered, as labels had to be read in different lighting and on imperfect surfaces. Error detection mechanisms were added to guard against smudges and printing irregularities. Those technical choices influenced how much data a code could carry and how compact the symbol could be. The practical limits of printing and scanning guided which designs moved forward. Over time, the simplest, most robust patterns were favored for high-volume retail use. A widely adopted retail standard emerged in the form of a uniform product code designed for supermarkets. Engineers created a numeric system and a complementary visual symbol to represent that data. The system assigned each product a unique numeric identifier to be used across retailers. The visual symbol used alternating dark and light bars to represent those numbers in a compact form. Scanners at checkout read the pattern and match the code to price information in a database. The choice of layout and encoding ensured fast scans even when labels were slightly imperfect. Adoption required coordination among manufacturers, retailers, and technology providers. Pilot installations demonstrated notable reductions in checkout times and inventory errors. Those practical benefits encouraged broader acceptance and stimulated the growth of compatible scanners and printers. The early retail standard set expectations for interoperability and shaped further developments. Parallel developments led to international variants and harmonization efforts. Different regions had their own needs for product identification and trade. Some codes use slightly different digit lengths or check routines to accommodate local numbering systems. International organizations worked to align numbering and symbology so that the same product could be recognized across borders. That alignment required agreements on how digits were assigned and how the corresponding bars were printed. Barcode labels had to fit on small packages while remaining readable by scanners in diverse environments. Standards bodies published specifications for symbol dimensions, quiet zones, and verification processes. These formal rules help manufacturers and label printers produce consistent marks worldwide. Conformity to standards eased international shipping and retailing. Over time, unified numbering systems reduced fragmentation and simplified global commerce. Beyond the retail standard, a range of one-dimensional symbologies addressed other business needs. Some designs emphasized compact encoding of letters and numbers for inventory and labeling. Others offered higher density for restricted spaces on metal or plastic parts. Alphanumeric codes allowed direct inclusion of product identifiers, batch numbers, and dates. Industrial applications often required robust scanning from odd angles and worn surfaces. Designers introduced checksum digits and start-stop patterns to improve reliability. Certain symbologies permitted variable length data while remaining simple to print. These alternatives complemented the retail code rather than replacing it, filling niches where different trade-offs were appropriate. The diversity of linear codes reflected the varied needs of manufacturing, shipping, and document handling. Standards and common practices guided selection of the right symbology for each task. As computing and camera technology matured, two-dimensional codes appeared to carry much more information in a smaller area. Designers explored matrix patterns that used both horizontal and vertical variations to store data. Those matrix codes could include error correction so that some damage to the symbol did not prevent reading. Data capacity increased dramatically compared with linear bars, allowing URLs, tracking blocks, and structured records to be embedded. New codes were optimized for optical imaging rather than single-beam scanning. That shift opened up reading by low-cost imaging sensors and mobile devices. The design choices balanced data density, printability, and error resilience. Industry adoption depended on compatible readers and agreed standards for encoding and error recovery. Two-dimensional symbols extended the practical uses of automated identification into new domains. One particular two-dimensional design became widely used for quick linking of printed media to digital data. The code used a square grid with distinct finder patterns at corners to assist alignment. Its ability to store web addresses and short messages made it useful for marketing and logistics alike. Mobile phone cameras and common software libraries provided easy reading on consumer devices. Error correction capabilities meant that codes could be printed on flexible materials or shown on screens with acceptable reliability. The open release of the specification encouraged experimentation and broad deployment. Industry groups recommended particular sizes and error correction levels for certain uses. Implementation guidelines helped printers and app developers integrate the code into labels and interfaces. The new code complemented existing barcode ecosystems rather than displacing them entirely. Standardization organizations played a central role in ensuring compatibility and trust. Member companies submitted technical proposals and practical requirements to committees. The process involved specifying symbol geometry, character encodings, and verification methods. International standards bodies produced documents that manufacturers and software vendors could reference. Those documents defined tolerance limits for printers and minimum quiet zones for reliable reading. Certification programs and verification equipment emerged to check compliance. Labels and supply chains were often verified before use to prevent scanning failures. Standards also covered data structures for item identification, GTIN allocation, and company prefixes. The steady work of committees and technical experts enabled global interoperability. That governance supported widespread adoption and predictable long-term use. The hardware used to read and print codes continued to evolve alongside the symbols. Early readers were bulky and used rotating mechanisms or fixed lamps. Laser scanners became common in retail because they could quickly read linear bars at different orientations. Imaging scanners and camera-based readers expanded the ability to read two-dimensional patterns and damaged labels. Thermal and inkjet printers provided practical means to place codes on packaging and labels. Print quality controls and verification tools helped maintain readable output in mass production. Mobile devices with built-in cameras turned phones into portable scanners for many applications. Advances in embedded systems and software allowed integration into point-of-sale, warehouse management, and manufacturing systems. Those improvements made barcodes and matrix codes usable in more places and under more conditions. In modern supply chains, the combination of standardized identifiers and automated capture supports tracking from factory to consumer. Unique item identifiers can be associated with production data, lot numbers, and expiry dates. Logistics handlers scan labels at key checkpoints to update electronic manifests. Retailers use the same identifiers to manage stock replenishment and sales analysis. Healthcare and pharmaceuticals apply strict standards for traceability and serialization to improve patient safety. Ticketing, access control, and digital receipts also make use of compact two-dimensional codes. The flexibility of modern codes allows a single label to carry a blend of identifiers and pointers to more detailed records and databases. That interoperability depends on consistent use of standards and agreed data schemas. The result is smoother movement of goods and clearer records across organizational boundaries. Looking ahead, barcodes and matrix codes continue to adapt to new requirements and environments. Higher density printing, better error correction, and new scanning algorithms broaden possible applications. Standards communities discuss extensions for security features, digital signatures, and richer data models. Integration with radio frequency systems and sensors offers complementary ways to identify items when optical reading is impractical. Accessibility and ease of use remain priorities for equipment makers and software developers. Consumer devices will likely gain incremental improvements in scanning reliability and speed. Many industries will continue refining how they allocate identifiers and structure related data. The steady evolution of codes is a practical response to changing needs rather than dramatic upheaval. The basic goal remains the same: to make identification simple, repeatable, and interoperable. The evolution of barcodes and standards shows a long arc from simple marks to structured identifiers and matrix symbols. Practical trade-offs between density, reliability, and printability guided each technical choice. Standards organizations and industry partnerships ensured that different systems could work together across borders and business sectors. Hardware and software developments opened new use cases and made reading more forgiving of imperfect conditions. The coexistence of one-dimensional and two-dimensional codes reflects the diversity of real-world needs. Many organizations now rely on standardized identifiers to manage inventory, verify authenticity, and enable traceability. The quiet progress of incremental improvements has made automated identification a routine part of commerce and logistics. Thanks for joining us for the evolution of barcodes and barcode standards. If you are still awake, please stand by for our next program.